Let's talk a little bit about time dilation. Let me just explain what it generally is in a shorter video, and then I'm actually going to derive the formula in another video here, if my bamboo pen will behave itself. Okay, so but here's the notion. Let's look at this clock here. The way this clock works, and this is a clock. This is supposed to be a spaceship that it's in, right? Okay, this clock, the way it works is that a little pulse of light leaves here, travels up here, hits the mirror, comes back down. Right, it hits the receiver and the clock goes tick. Okay, that period of time, since it started here and ended there, and these locations did not move with respect to us, this is actually called the proper time. This is time registered by a clock that's not moving with respect to us. Tick happens at the same place as tock. Okay, the proper time in this case is twice that distance, right, divided by the speed of light. That's the proper time. Okay, now let's suppose we get the clock moving. Proper time, yeah, I already said that. Okay, let's suppose we get the clock moving. Remember, proper time is twice that distance divided by the speed of light, right? In this case, though, if the clock's moving past us, right, now the light actually follows this longer path. Like that. By the time it hits the mirror has moved L distance, right? And so the distance the light travels is the square root of d squared plus L squared. Well, that's bigger than d. Okay, so the time it takes this light to travel is, and of course this light doesn't travel any faster than the speed of light. It's true that remember the postulate of first postulate or second postulate of special relativity is that light is always observed to be traveling the speed of light. So this light travels the same speed but travels a greater distance. So therefore this takes a longer time. The dilated time in this case would be twice the square root of d squared plus L squared. And that's over c. This will be a longer time. Okay, in the next video, which you could skip if you want to, but it's a major triumph of high school algebra, I'm going to derive the formula with the Lorentz factor in it from this whole expression here, which is very cool. But the point here is that a moving clock, okay, this moving clock here ticks more slowly. In fact, any clock, whether it's designed this way or not, ticks more slowly. In fact, time itself travels more slowly in this frame of reference. As they go by, we see cheese mold slower, people age slower. Okay, and so in this frame of reference, time itself travels more slowly. Time is a relative thing, which is very cool. Usually we don't think of that, but it's true. If we go close to the speed of light, particles that decay in a very short time take a bit longer to decay. We've done this. This is not pie in the sky. This is actual stuff that really happens.